And what you should see, is that you put back in the box when we afterwards.
Can you get like three things here?
No, what you get is what you can see here quite clearly. Sorry for coming over here, but I'll give you to sit down here and show you quite clearly. What looks like is happening is there are waves along this direction. There are waves along that direction. There are waves in the straight through position, and there's waves there. But it looks as if in these positions here, and here, and here, and so on down there, what's happened is the peak of one wave has met the trough of the other one. And the water is actually still. The water's not moving. In these places here where you've got the waves, what you've got is you've got two peaks joining together, or two troughs. So what you see, if you were to look at this side here with light waves, along here you would see light, dark, light, dark, light, dark, light, dark on the screen. I know it's incredible. Richard Feynman said that with this experiment, with a double slit experiment, which was voted by the Institute of Physics members as the most beautiful experiment when done with single electrons, is the problem where all quantum mechanics starts from. Because what happens is you're adding light to light, and when you add light to light, you get no light. I mean, isn't that just absolutely phenomenal? How can you add light to light and get no light? But that's exactly what you get with a double slit experiment. Okay? Now, you talk to Sally or I, right? You might think light is just that visible part of the spectrum, red, orange, yellow, green, blue, indigo, violet. But for Sally and I, when we say the word light, we understand everything from radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. To us, there's no difference between any of those waves except for their wavelength. So what I've got is a transmitter and a receiver, and when I pick it up, this one is set up to produce the waves, and this one has an internal modulator. So what it automatically does, when it picks the waves up, it gives out a 1 kilohertz sound. It makes a sound that's a bit, we put those back in the box.
Oh, yeah.
It makes a sound that's very similar to this.
So it's not going to help us do anything with this.
No. So, that one's on. That one's on. There's no microwaves here.
So the microwaves are coming out in this sort of direction, yeah?
Yeah, absolutely. And when I bring that in front, got microwaves. What else can I do? Well, I think you know by now. Yeah. I can do that. Yeah. And when I get the angle just right, make it a bit closer. There's no signal there. Very little signal there. But when I get the angle of incidence equal to the angle of reflection, I'm actually reflecting the microwaves. Okay? So obviously if I put something in between, nothing goes through. Just put a little one here. And I put a piece of wood in front. What happens? It goes through the wood, right? Yeah. So what does this tell you then? Well, I'll tell you something. It's not right, okay? Just so you remember. I always love that one.
And we don't have to worry about him pushing his brain, because the microwave frequency of an oven is to make the water molecules oscillate. So it's much lower frequency than this. Still microwave.
Do we want to just show?
No, that's the latest.
That's the latest.
That's the 95.
Okay, right. So what we can do now is, there's a complete analogue now of what you've just seen. Is there not?
So what are we doing now?
What are we doing now?
Yeah. So what we hope now, we know we're going to get a cut down in intensity because we're blocking a lot of it. But what we're hoping to do now is bend it.
So that's about 2.8 centimetres, right? Obviously you're not in the straight through position, but look, there's still a signal there. So it's the waves have come through and they've bent round. I think we've got a little probe in there which works even better than this, but that one works quite well. Right, okay, we've got one more experiment we can show you. I can put this.
I used to work in a lab where they had a lens microwave.
Yeah, lens.
And it was made of wax.
Yeah.
It was a great big yellow wax lens. Because obviously that was the material that you could use in order to refract microwaves, so refracted through.
I know it's bends, but why does it bend?
Because it is.
Yeah, I know it does that, but why does it bend? What bends it like to make it bend like that?
Well, you can. We talk about this a lot when we
Yeah.
coherence, because we've got 1, 4, 2, 2 gas. And what you've got to imagine is that we've got, if we could see them, they would look like that. With the destructive and destructive.
So just like you saw the water waves, you've got peaks, and then you've got water, and then you've got no water. There's a signal there. If I move it round, there's no signal. Can you hear the signal again? No signal. Signal again.
So, and what's interesting is if we could measure the distance, the position, if we've moved around between signal and no signal, we could go back and find out the... If you close your eyes and you've got your probe, you've isolated your probe, which is you've got one ear working, and if you just sway backwards and forwards, because of the wavelength, the sound waves, you should actually be able to go just in one sway from quiet to from a minimum to a maximum.
That's not too bad, everyone. It is, yeah. Is it going up and down? It's quite good, isn't it? Yeah, it is. I can hear it. Can you hear it? Oh, sorry. Not for long. Here it goes. Here it's up now?
Very long.
Keep going. Very good,